So welcome to the design where I wrote locus and compensation techniques. So in this lecture we will discuss about lag compensation. So we discussed about PI compensation or PI controller that is used to design for the desired steady state error performance. We said that PI controller or ideal integration controller is an active system. It requires power source. However, this lag compensation is a passive system that doesn't require external power. So in case of PI controller, we were able to find the zero steady state error by putting the pole at origin. But here in case of lag compensation, we put the pole near the origin and a 0 close to that pole to the left side. So here is not the pole on the origin but close to the origin. So in case of lag compensation, we can get the finite steady state error but not the zero steady state error, because the pole is not on the origin but it is at some finite distance left to the origin. So we can see that this system, if we have such a system, like we have this gain and we have this GS, and GS if we can write in terms of S plus Z1, S plus Z2 and so on upon S plus P1, S plus P2, so on. So we have, this is our GS and we have CS so minus plus this. Okay. Now this is here gain and this is here plant. We want a compensator here, so we replace here to add a lag compensator. So lag compensator here we will have to put S plus ZC by S plus PC. So now we can see that here this is not a type 0 system, but this is not type 1 system after adding this compensator. So let's take it as here in the beginning type 1 system. So this plant is type 1 system because there is one pole at origin and we want to add a compensator for this type 1 system. So because this is type 1 system, we will have the static error constant Kv, that is velocity static error constant, and here we will have Kv, we say Kv0 equal to K Z1 Z2 upon P1 P2. Now the new static error constant Kvn equal to, so K Z1 Z2 upon P1 P2 into, so here ZC by PC. So this is equal to K V0 into ZC by PC. So we see that the original system that has a root locus if we take here these three poles, this was the root locus of this system. And we had some point P here. And this was the angle. We want to improve the steady state error. We want to reduce the steady state error of the system, but at the same time we want to retain the transient response. So therefore, if there is some point P with certain transient response, we want that the root locus passes through this point P even after adding these compensator. So the new root locus will be, we have added this we add this pole and this 0. Let's take the minus sign here, S plus ZC equal to 0, so S equal to minus ZC. So when we are adding this compensator, what will be the root locus now? The new root locus. So we will have one pole near the origin, that is minus PC. Then there will be 1 0 minus ZC near to this pole, and then these are the 3 points, 3 open loop poles here. So this root locus will move like this will move and break away, and this will go to finite. So now this root locus will be and here it will again, the point P is on the root locus. So now the angles, here this is angle theta PC and this angle is theta ZC. So here this point we are adding this root locus, here we are adding one pole and 1 0 here near to the pole, so that this angle that is with this pole and the angle due to 0, they have opposite sign and they will cancel each other. Their effect will be very less, and this point P will be still on the root locus. So we will not affect the transient response by adding these poles and zeros in order to improve the steady state error. And we see that this point P, the gain will also not change because these points are closer. This length of these this P and this 0 and P to this pole will be same and they will be cancelled out, as well as the angles are closer, so their effect will be cancelled out. So here we obtain this KVN equal to KV0 ZC by PC, and that is greater than KV0. So we see that here ZC is greater than PC in magnitude. So therefore KVN is greater than KV0, and we know that steady state error is 1 by KV. So if it is greater than earlier KV, so steady state error will be less than the earlier uncompensated system. So for example, if we put PC equal to minus 0.01 and ZC equal to minus 0.01. So ZC by PC equal to 10. So here we can see that these PC and ZC are very close to the origin, and so they are, and however they have the 10 times the 0 is 10 times farther than the pole, and so we will get here KV and 10 times the original uncompensated system's KV, and so the error we will get 10 times reduction in the steady state error, and this will satisfy these angle conditions here. So we see that the ideal integral compensator can lead to the steady state error 0, that is PI controller can lead to the steady state error 0, but the lag compensator will reduce the error in this ratio, that is ZC by PC, because here we can write one by KV0 into ZC by PC, and that is, so here KVN. So here we can write 1 by KV0 is E infinite of the uncompensated system by ZC by PC. So here we can see this is, if this is 10, we can have the steady state error 1 by 10 of the uncompensated system. So this will reduce the steady state error, this lag compensator, in the ratio of ZC by PC, and it will provide the minimal effect on the transient response because these two added pole and 0 are very close to the origin. Now we will take one example to understand this. So let's take one example. So here we have a system. We have to compensate the system whose root locus is shown to improve the steady state error by a factor of 10 if the system is operating with a damping ratio of 0.174. So we have a system here. So this is gain and this is plant. So here we have to find the steady state error. We have to improve the steady state error by a factor of 10, and the system is operating at damping ratio 0.174. So first we must find that what is the steady state error of the uncompensated system. Then only we can know that what is the objective or of the steady state error, that is 1 by 10 of the current steady state error. So for this we have to find the Kp, and we can find that when we have a system and we have this line 0.174, and we have here -1, -2 and -10. So we have a root locus that is cutting this line, and this root locus. So here it may cut this line A, and that is 0. This A is 0.694 plus J 3.926 for K equal to 164.6. So this point, this root locus is cutting for this damping line at this point 0.694 plus J 3.926. So we can find that this Kp, because this is the type 0 system, so the Kp we have to find the static error constant. So Kp equal to Gs, here limit s tends to 0, and that is equal to, here K, the total system is K by s plus 1s plus 2s plus 10. So K by 1 into 2 into 10. So K is 164.6 by 20. So we get 8.23 this Kp, and so uncompensated systems has the steady state error 1 by 1 plus Kp, that is 1 by 1 plus 8.23, and this is 0.108. So this is the steady state error of uncompensated system. Now the desired steady state error of compensated system, that is equal to 1 by 10 of 0.108. So that is equal to 0.0108. So what will be the value of Kp for to obtain this? So Kp equal to, we can use this here, and Kp equal to, we will have 1 minus E in steady state error. So 1 minus 0.0108 by 0.0108. So this Kp value we obtain is 91.59. So we must have this value of static error constant if we want to satisfy the steady state error design. Now we know that ZC by ZP equal to Kpn by Kp0. So this is Kpn and that is Kp0, because we want to know the zero and pole location of the compensated system, lag compensated system. So here we will have, we know this relation, that the ratio is equal to the, we developed for earlier case Kvn by Kv0. Similarly it will be Kpn by Kp0, and that equal to 91.59 upon Kp0, that is 8.23, and so we will have 11.13. So here now we can select some value of here it is Pc. We can select some value of Pc. So because this is a design process, we can take some value of Pc that is close to the origin. So if we take Pc equal to 0.01, so if we take here Pc equal to 0.01, we can find Zc equal to 0.01 into 11.13. So we get 0.111. So now we can plot this compensated system root locus. So here we can have this system root locus. So now we have here Pc equal to at 0.01 minus 0.01, and this is Zc equal to minus 0.111, and the other system poles are at -1, -2, and then -10. And we have here damping equal to 0.174 line, and we can see the root locus here. It starts and ends to this 0. Here it will start here, and this will start and go to infinity. So this root locus will go and cut this line, and it will cut at this point. So it cutting minus 0.678 plus J 3.836 for the value of K equal to 158.1. Of course, here will be the another point and other pole will come to this side. So the lag compensated system, we have the lag compensated system. So the lag compensated system will be here. So we will have one K S plus 0.111 upon S plus 0.01, S plus 1, S plus 2 and S plus 10. Here K equal to 158.1. So this is the lag compensated system. And if we find the Kp, value of Kp for this system, so value of Kp equal to, so 158.1 into 0.111 by 0.01 into 1 into 2 into 10. So this is Kp. When S tends to 0, we can calculate this value and we will get that this value of Kp is 9.818. So this is the value of Kp, and when we want to, we can calculate the steady state error from here by 1 plus Kp, and when we compute the steady state error, we will get this as 0.011. So this was our objective, and we obtained this steady state value error value by lag compensated system, and we maintain this point on the damping equal to 0.174 line. So here the values of K we get 164.6 and 158.1, and Kp is we are getting for uncompensated system 8.23, and for lag compensated system we are getting 87.75. So I think here is some mistake, and we can have this value at 87.75. So there is this mistake, that this is not this value. So we can have Kp 87.75, and this thing we can see here in the this table. So we have this system uncompensated, this is compensated system. We have K here was 164.6 when this point was on the damping equal to 0.174 line. Here it is 158.1. This is Kp, and here we can see the response, that is uncompensated system and lag compensated system. So we can see the response of this lag compensated, that is improved the steady state error, but not the zero steady state error, but there is some finite steady state error. So this example was taken from the Norman S. Nice Control Systems Engineering. So I thank you for attending this lecture, and see you in the next lecture.